Let's start. Lesson 10, the laws of thermodynamics. We will be able to describe the first two laws of thermodynamics. So our goal today is to talk about what those two laws are. We're not going to go into the calculations that you can do with those laws. We're just going to talk about basically what they are. And when we talk about the first two laws, there are actually technically almost 4 laws of thermodynamics, even though people often say there are 3 laws. We're only going to be talking mostly about the first law of thermodynamics. We're not going to go deep into the other types of thermodynamics, but if you want to, you're more than welcome to look up those in your own time. If you're interested to watch some YouTube videos and see what they say about them, we're just going to stick to the first 2 principles of thermodynamics. So that's going to be our goal today. I'm going to keep this up for a little bit longer. So yeah, I've also got a wake on board at the moment, guys. So that means I can pretty much write whatever I want on these slides. So that's pretty useful. Let's go back a second to talk about what we discussed last lesson when we were in class. The last time we were in class, which was on Thursday, I believe, we talked about, it was a big lesson because it was double. And in that, and was also that was also when, for those of you who were here, we did a little mini demonstration. There was convection and radiation we talked about. We said that convection is the transfer of heat through a substance. The idea of convection is that, oh, Minvu just joined, okay. The idea of convection is that when hot, where is a better slide that talks about it? I think the next slide is a little bit better. So the main idea of convection from last lesson, no, yeah, sorry, my computer just tried to do something weird. I'm hoping you can still see the PowerPoint. The idea is that convection says that this air is less dense. The reason it's less dense is because it's hot. And what do less dense things do? They tend to float. Why is it less dense? Because the particles are moving faster. So they are more further apart from one another. Whereas down here, the particles are cool, so they are more dense. And what happens in more dense is because they're not moving as much, you can pack more of them closer together. That's why they are more dense. So that's why this idea of density links with temperature. You should also remember, we've already discussed how temperature links with density when we talked about metal expansion. When we said that when you heat a metal, it expands because the particles take up more heat. That metal is, the material is taking up more heat, so therefore that metal is slightly less dense because it's been heated up. So it's the same sort of idea. Now, as this hot air fills up this area of the room, it gets it gets full. And then as that air cools down, it goes down. And so on and so forth. And then, of course, that'll cycle around. Question in the chat was, if things usually expand when they contract when they get heated, why does ice get bigger? Actually, a really interesting question. Surprisingly enough, it's actually a chemistry, more of a chemistry question than it is a physics question, but it does still apply. It turns out that the crystal structure of water takes up a greater amount of space than the crystal structure of than the liquid structure of water. So the liquid structure of water, pretty much the water molecules can go wherever they want. But with the crystal structure, because they're fixed, they take up more space. Water is actually rare in that. It's actually very rare that something will take up more space. And that actually is what allows icebergs to float, and it actually probably in some ways allows a lot of life in the earth to actually exist. Is just the mere fact that ice floats, which is a weird thing, but still. Talked about, so then this makes something called a convection current. Same idea here. And then the only difference is then we looked at applications. Well, in the atmosphere, the air heats up when it's close to the earth, it goes up, and then the cool air sinks over the ocean and pushes in. And this is what we can think of as a coastal draft. And the opposite happens at night. And in the Earth's crust, again, that same cycle, you will have a hotter pocket which pushes up, and then that's going to cool down and sink. And that creates, again, another cycle. In fact, this is the cycle that the tectonic plates float on. Then we talked about radiation. So radiation is just anything that's above 0 degrees Kelvin will emit some kind of electromagnetic radiation. Now, electromagnetic radiation can be anything from infrared light, which we pretty much refer to as, heat, all the way up to visible light, ultraviolet light, even X-rays. If you can get something hot enough, then it can emit X-rays. But I guess hot is a weird term when you're talking about X-rays. So you can think of that, right? You can heat up a pan, and you can feel that it's hot without touching the pan. You can feel that it's hot without the convection going on. If you heat up something really hot, you can actually get it to glow. And that would be like if you think about heating up a piece of steel. In a blacksmith, you can get it to glow red and then even glow white. So that's sort of this idea of emitting radiation. But even you and I are emitting radiation right now in the form of infrared. Might not be a lot, but we still are. That infrared radiation can be either absorbed, emitted, or transmitted through objects. And then we talked about why, white shirts are really good at emitting light, whereas black shirts are really good at absorbing light, and so on and so forth. And then that was pretty much it from memory. We talked a bit about how the wavelength of light tells about the energy, but I quickly sort of pushed through this. So I didn't want to dwell too much on this. I just wanted you guys to get the idea of shorter wavelength, higher frequency, high energy. Whereas longer wavelength, low energy, low energy. So that's the main idea I wanted you to get from that slide. And then we sort of talked a bit about this, and I did warn you guys, it's a little bit hand-wavy. The reason that things emit light when they're hot is because ultimately the electrons are being bumped around. And when you bump an electron around and it moves from one place to another, it will emit some form of energy. And that form of energy will usually be in the form of light. Think about this. You already know that when electrons move, they emit light, because if you remember when we did the flame test back in year 9, when you squirt like certain atoms into a flame, the flame changed color, and that's because it was specific electrons getting de-excited. Then we talked briefly about, how you can cool a computer using a bunch of these principles together. And then that was about it. So today's lesson, we're going to talk about the thermodynamics of the law of thermodynamics. So we're going to talk about the first 2 laws. The first one's a bit basic, and yeah, the idea of the first one might be that the idea of the first law might be that you go, oh yeah, that makes sense. That's pretty logical. That's the point. It's supposed to be really basic, but it's still really important to understand because it is the basis of all other types of theory. So we're going to talk about thermal equilibrium first. Thermal equilibrium means 2 objects are touching and are the same temperature. That's all the thermal equilibrium means. So I've used this term a lot in the past couple of weeks, but I've never actually properly defined it. So if you have an ice cold drink, and you have a really warm table because it's been out in the sun, those are not at thermal equilibrium because one is a different temperature to the other. But if time goes on, and as time goes on, the we'll say the table gets a little bit cooler, and a bunch of the energy goes from the table into the drink, and the drink gets a bit cooler, and they have the same temperature. Let's say that's 20 degrees and that's 20 degrees, whereas here we'll say this one on the left is 25, and we'll say this is maybe we'll say this is chilled, so we'll say this is 5 degrees. So they reach the same temperature. That's what thermal equilibrium means. Okay, in fact, if you think about it, right, and this is one of the questions that you guys will be answering in the next little bit, is if you think about a thermometer, right, thermometers don't actually directly measure the temperature. You might be like, what do you mean thermometers don't directly measure the temperature? So if you think about a thermometer, right, if I put a thermometer into some water, right, what's going to have to happen is that it's going to have to come to thermal equilibrium with the water before it measures the right temperature. You might be like, what do you mean by that? I sort of mean is that if you put a thermometer into water and then you try to read the temperature straight away, you get the answer wrong. You have to wait for that thermometer to reach the same temperature as the liquid before you go, oh, well, now they are, now it's at thermal equilibrium. So now this thermometer is telling the temperature of the water as well as the temperature itself. Sometimes that might be a little bit of a random sort of point, but it's true. Thermal equilibrium takes time. It's not instantaneous. And that's probably a good thing, because you wouldn't want your drink, if you take it out in the sun, to go straight to being really, really warm without you being able to drink it. So it takes time for it to come to thermal equilibrium. What is the first law? Well, we don't call this law the first law of thermodynamics. Refer to this law as the 0th law of thermodynamics. What the heck is the 0th law? They call it the 0th law because it's not one of the fundamental laws of thermodynamics, but you need to understand this law in order for you to sort of get the basics of the rest of it. And I copied this law has been copied from many different places, and it's one of the most confusing ways to write this law that I've ever seen. But I'm going to give you guys the full explanation first, and then I'm going to give you guys a better way to think about it. So the full explanation is, if two bodies are in thermal equilibrium with a third body, then the first two bodies are in thermal equilibrium with each other. What that means is that if body A is in thermal equilibrium with body B, meaning that body A is the same temperature as body B, and body C is in thermal equilibrium with body B, meaning that body C, so body A is in thermal equilibrium with B, and body C is in thermal equilibrium with B, then that means that these two, by definition, have to be the same temperature. And it just says eventually they're all the same temperature. I'm going to keep this slide up for a bit. I'm going to let you guys try to understand this, and then I'm going to give you guys my alternative explanation of this, because I hate this explanation. I think this explanation is dumb. It might not be dumb. I might just be really bad at teaching it, but I've got a different way of explaining it. I will, don't worry, man, I'm going to explain it again, but I'm going to explain it in my own way. I'm going to change the slide in about 20 seconds. Those of you that want to write down this formal definition here, you can. The next slide is going to have a different way to explain this same thing. So it's not new content on the next slide. It's just a different way to explain it. The way that I prefer to explain it is not with like object A and object B or body A and body B, because then it gets a bit confusing. I like to explain it with tangible items, like physical things that we can think of. So the way that I usually do it is I do it like this. I use rock, paper, scissors, because we all have played rock, paper, scissors before. This has absolutely nothing to do with the game rock, paper, scissors, but I liked having physical things that I could say, yes, we all know these three objects. So let's just say a piece of paper is 25 degrees. A piece of paper is at the same temperature as a pair of scissors. Okay, we know that the paper and the scissors are in thermal equilibrium with each other. Okay, even without a thermometer, even without being able to measure the temperature, we just know that they're in thermal equilibrium. Maybe they've been sitting with each other for 2 hours, and so we just know that the paper and the scissors are the same temperature. That's fine. But let's say that we also know that the pair of scissors happens to also be in thermal equilibrium with a nearby rock. These two are also at the same temperature. And the reason that those two are at the same temperature is because maybe they've also been sitting with each other for like a long time and they've reached thermal equilibrium. So if the idea is, if this is 25 degrees, because it's in thermal equilibrium with this, which is 25 degrees, and which is in thermal equilibrium with this, which is 25 degrees, the theory is that, well, you could also say that these two are in thermal equilibrium with each other. The rock is the same temperature as the paper. These two are also in equilibrium with each other. Now, if this makes you say, yeah, duh, no shit, I get that, that's kind of the point. The point is just to say that if you know that, it's kind of a weird argument to make, but the point of this argument is to say is that if you know that two things are joined, then you don't need to know that the third thing is also joined. And this gets used a lot in other types of laws, because what you will say is you'll say, okay, well, this object is in thermal equilibrium with this, and this happens to be in thermal equilibrium with that. So even though the paper and the rock may never have touched, because they both touched the pair of scissors and they're both in thermal equilibrium with the scissors, then you know that they must be in thermal equilibrium with each other. It's a bit of a weird idea, but it's also a really basic idea to sort of explain. Does that explanation sound a little bit better than saying body A and body B? I think so. I can go back over this again, but I don't know how much more I can add. Are we good for me to change the slide? Let me know. Yep. Okay, I'm going to change the slide now. So that's the 0th law. So that law doesn't really count as a law, but it's still there because we use it a lot, especially when we're talking about temperature moving. It makes sense to be able to say, oh, well, this temperature and this object are already at thermal equilibrium because they're both the same temperature as this object in the middle. The first law of thermodynamics. Now we're going to be spending the next double period all about this law, but I thought it would be a good place to start would be to talk about this law now. So what is the first law of thermodynamics? Energy is conserved and cannot be created or destroyed. Now that's a rule that you guys have probably heard time and time again, especially when we do learn lessons about energy conversion. It's like, oh, energy can't be created or destroyed. But I guess the real important part about this is not really energy can't be created or destroyed, because people obviously always remember that, but energy is conserved. All energy must be accounted for. When we say energy can't be created or destroyed, that's what we mean. Is you can't just go, oh, well, you can't just go, we had 5 joules of energy at the start, and at the end we had 2 joules of energy, you have to say, well, where is that extra 3 joules? Where is that energy gone? You have to be able to account for it. You can't say, oh, that extra 2 joules that was destroyed. Like, no, it can't be destroyed. Where did it go? You have to account for it. This is kind of like, this law is kind of like the accountants of the energy. So then the other part is, well, I'll jump to that in a sec, sorry. So the idea is that this allows us to do something. We can always go the energy before and the energy after are the same. So you can actually start to do some maths with this. You can start to say, well, if I know how much energy there was at the start, and I know that some of the energy is in this form, I know the rest of it has to be in the other form. They have to equal because all the energy has to go somewhere. If you burn some wood and it makes a bunch of heat, or or it makes a bunch of light, where does all the other energy go? You have to be able to attribute it to something. Now, we've learned how internal energy exists in a system, which we will represent using the symbol U. So internal energy, we're going to use the symbol U. And this is sort of giving us the basics that we can use, because what we're going to be doing is we're going to be using this idea of this maths. We're going to say, well, if we know how much internal energy there was at the start and how much internal energy there is at the end, because of the first law of thermodynamics, we have to find out where this remaining energy went. Now, we already have, and of course, that internal energy can be changed in 2 ways. The internal energy, remembering, is the pushing, the stretching, the rotating, the moving, the translational motion. And that energy inside of a system can be changed in 2 ways. The first way is the way that we just spent all last week talking about, which is heat transfer. The first way that you can change the energy in a system is by either putting energy in by the form of heat, or taking energy out as a form of heat. So that's like saying, if I've got a can and I heat that up under a flame, then that's going to add energy in. The energy of that's going to go in, the internal energy of that's going to go up. But there's another way that you can add energy into a system, and that's a method that we haven't discussed yet, and that's called work. And that's what I'm going to spend the end of this lesson talking about, is what work is. I'm going to keep this slide up for another 30 seconds for those of you that want to copy this down. And then what I'll do is I'll jump, or maybe not copy this down, but take some notes. And then what I'm going to do is I'm going to jump to the next slide where we talk briefly about work and what work is. But are there any questions about this first law? The key to this first law, as I've said already, is this word here, conserved. A lot of people remember, oh, energy can't be created or destroyed. It's like, yeah, but that's not really useful. Like, so what? The key word is energy must be conserved. You must be able to account for all energy at the beginning, at the end. You can't just cheat and say, oh, this bit has more energy because the energy just got created. Or this bit has more energy because, I don't know, the energy got destroyed. You have to be able to account for all of the energy. So, what is this idea called work? We've talked about heat transfer. You can't just introduce this idea of work without explaining it. Work, W for work, is the symbol that we give for work. Another way that energy can change a system is by doing work. Okay, so I talked about how energy can go into a system via heat transfer, but energy can also change in the system because of work. Work is a measure of the energy transfer as an object is forced over a distance. So whenever your system does work, it's actually pushing against something or pulling against something, and it's losing energy because it has to push or pull. The example that I like to use here is just this bag of popcorn. Because when I first thought of it, I was like, oh yeah, that's actually a great idea. As that popcorn expands, it takes up more space, but it has to push against the bag to get more space. And as that pushes against the bag, it will lose energy. It does work on the bag. It loses some energy because it has to push against the bag. Another example would be a balloon. As a balloon gets blown up, it takes up more and more space, and so it has to push on the rubber inside of the balloon in order to get to that size. It has to push against the air. If you think of an explosion, right? An explosion pushes against the air. It does work because it has to push against the air. So it's going to lose a little bit of energy because it has to push things out of the way. It's actually that work that makes an explosion dangerous. When an explosion goes off, it's pushing against the air in the room, and so it's pushing things over. It's creating wind and that kind of thing. And the shock wave is essentially the work that that object is doing on the system, doing on the environment around it. So that's what we mean by work. Sometimes, of course, we're going to talk about this on tomorrow, but we can use this work to our advantage. This is how, of course, if we can harness that explosion and put it into some kind of tank and then put a piston on it, we can create an engine. And that's, of course, that engine idea is what we have. Josh, that engine idea is what we use to make cars work. Are there any questions about what work is? If not, then ladies and gents, that's it for today's lesson.